Okay, so for those who have joined for the first time, I can again introduce myself. I'm a PhD at IIT Kharagpur. I'm working on development of composite cylinders, and this is the doubt solving session which is being offered by NPTEL itself. And in this doubt solving session, you can post doubts related to the like topics which are taught in the previous week, and I'll also be discussing the assignments which have already been given, like whose solution key is already available in this course, and also the doubts which will be posting into that ask a question column of that NPTEL website, that also I'll be solving. So if you have any doubts related to composites which you come across in your daily life, or when sir is explaining in some of his lectures, then you can just post it there and I'll discuss it in this doubt solving session on every Monday from 6 to 7. Fine. So um, let's start. Okay, so today I'll be explaining the answers of the assignment 2, which has been posted in the website already. So let's start with the first question. So the first question was, which of the following statement is true for glass fiber? So the statements are as follows. The first says that as compared to carbon fiber, glass fiber has less elongation before breaking. So this is the common properties of all kinds of fibers which is compared, that is baggage. This is the waste which is left out of sugarcane, then cotton. All these kinds of natural fibers are there, and there is also e-glass and carbon fiber. So we can see elongation at failure, that is equivalent to elongation before breaking. So this in case of e-glass is 2.5, while in case of carbon fiber it's 1.4 to 1.8. So glass fiber has higher elongation at break, and therefore this first statement is wrong. Then when we come to second question, then says that viscosity plays an important role in the manufacturing of glass fiber. So this is the manufacturing process. We can see here the glass is molten, then filaments are made by simply flowing these molten glass through small holes, and these fibers are then collected and bound together to obtain yarns as per our requirements. So if the viscosity is very high, then in that case the fiber will break in between. But if the viscosity is quite low, then it will flow very easily, because viscosity is the resistance of the fluid when it's flowing. So if it's very low, then there would be a lot of small droplets which would be forming instead of long fibers, and if the viscosity is very high, then the fibers will simply break and there would not be continuous fibers which could actually serve our purpose of like making carbon fiber, glass fibers. So that's why viscosity plays a very important role when we are trying to melt glass and manufacture these glass fibers. And the third point was humidity is an important factor influencing tensile strength of glass fibers. So it is already well known that glass reacts with water. As the surface area of glass fibers is quite low, then its reactivity is even higher, and thus the moisture simply gets into the micro cracks and depletes the overall surface. So therefore, tensile strength will directly be affected if moisture is present in the environment. And therefore, statement 2 and 3 are true, while first is wrong. And that's the answer which is given in the solution. So the second question was that if the statement is correct. So in this one, it's we already know that graphite is around 99.99% pure carbon. Like graphite fiber is almost 100% carbon, while carbon fiber is around 90 to 95% carbon. So when we compare these two properties, the percentage of carbon in graphite fibers is very high as it's highly pure substance. Therefore, it's crystalline in nature, and therefore graphite is crystalline while carbon fiber is amorphous. So the first statement is correct. So this is the this is a statement which is out of the manufacturing process of graphite fibers. It states that once carbon fibers are produced, then we again heat them at very high temperatures so that a more crystalline structure can be formed, which has higher elastic modulus. And this is how graphite fibers are formed once we obtain carbon fibers. So therefore, graphite is more crystalline when compared to carbon. Its purity is also quite high. Then uh, Then we have the next question. It states that glass fibers are useful thermal insulators. Now, the reason behind this assertion they've given is that glass fiber has high ratio of surface area to weight. So, the purpose of these kind of questions is that first is the assertion, that is a normal statement. Then we check if the second statement, which is termed as the reason, is the correct explanation of this particular statement. So as we can see here, it states that glass fiber are useful thermal insulators. Now, when we are trying to compare glass fibers with carbon fibers, then on the basis of the thermal conductivity of these two materials, that is glass and carbon, we can say that glass fibers would be better insulators as compared to carbon, as carbon in form of graphite is definitely one of the best conductors which we can have, while glass is a popularly known insulator. So on basis of material, it is a thermal insulator. But this reason states that glass fiber has high ratio of surface area to weight. So this statement can also be correct if we are comparing glass fiber with glass sheets. So when we compare the thermal insulation strength of fibers as compared to sheet, then fibers are better insulators as compared to sheet because fibers have higher surface area. If the surface area would be higher, then the conductivity, absorptivity of any material would be far higher as the same material if its overall surface area is lower. So if there are a lot of carbon fiber like glass fibers present in a medium and we apply heat at one end and it is said to pass through this entire medium and be transferred to the other end, then all the glass fibers which are present in between will have higher surface area, therefore their absorptivity would be quite high, and the amount of heat they'll be storing within themselves will also be quite high as compared to a single glass sheet would be which would be present at that particular surface. And therefore the glass fibers will have high thermal insulation due to their high surface area to weight ratio. And therefore, considering this particular explanation, we can simply say that this particular reason absolutely fits into this assertion, and thus first is the right answer. Please note, yeah, 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 yeah. But what we see is that there are matrix materials in between, right? You'll not directly be using only carbon fibers when you're considering an entire composite. There is matrix material in between. So if you have a laminate composite, that is glass sheets are there, matrix is there in between, that is resin. So we have like a square sheet like this. It's glass sheet. Then we have resin parallel to this one. Then we have another glass sheet. All these are there in series. So conductivity would be when we are transferring heat from this end to this end. But absorptivity would be how much heat it would be storing within this material and how much heat it would be transferring to this end. While matrix along with this combination will provide insulation. Are you like clear with this? These are two different things. One is yes, yeah, Yeah, and as the surface area is higher, its absorptivity will increase. So therefore, the heat it will store will be far higher as compared to the heat which will be stored by a glass sheet. So that's why your like fiber and sheets, these two will have different conductivities. Are you getting it? Okay. So then there's another thing which is added to glass fibers during their manufacturing itself. So when we are using glass fibers as thermal insulators, then we coat these glass fiber with an extra bonding agent which trap a lot of air cells within and thus improve the overall insulation further. So this is an extra information. This doesn't directly correlate with this, but yes, if you are specifically purchasing glass fibers which would be used as thermal insulators, then compared to normal glass fibers, you should go for glass fibers which are coated with bonding agents or sizing agents which support um, like trapping materials which would increase its insulation further. Like, this is not completely correlated to this question, but it's yes, an extra information which if you are there in this course, you should know that whatever extra things which could be used and incorporated into our design further so that our composite design is even better and its performance is high as per our applications. So now we move towards the next question. In this, these three questions in this particular assignment were related to the manufacturing method of carbon fibers. So we see here, um, this is what sir explained that initially we take a source which is a high concentrated carbon source, then we melt it, and then using melt spinning we obtain carbon fibers. Then we stretch them under a tensile load along with simultaneous heating, which is known as oxidation. This is for the stabilization process. Then it is pyrolyzed in presence of only nitrogen. And here it's the carbonization process in which all the impurities are removed from the medium. And then finally, we like if we want to make graphite fibers, then we'll do graphitization so that the percentage of carbon will increase even further, and finally we'll obtain graphite fibers. So this is the common workflow which is given in this melt spinning, oxidation, carbonization, graphitization is the direct steps which would be involved in production of graphite fibers, and this third is the right answer. Then in the next question, it was asked that during production of carbon fibers, carbonization is used. So as sir has already explained, it is the process in which the carbon fibers are heated at very high temperatures so that extra impurities and like non-metallic elements are removed from their like surface or within their medium also. So that's why this is used for removing non-organic elements, and thus third is the right answer. These questions were quite direct, so I don't think I need to explain a lot in this. And the ninth question was also based on the same method. In this, they asked that in carbon fiber production process, the oxidation is known as the stabilization process. So this sir has already explained. It produces fiber that are stable at high temperatures of carbonization and graphitization. So yes, it's correct because in case of carbonization, you'll actually heat the carbon fibers at 1500 degrees Celsius. It's very important to stabilize these carbon fibers before this treatment because carbon fibers inherently start degrading at 400 to 450 degrees Celsius. Right now they have impurities, so definitely they would not degrade at such low temperature. However, we initially need to stabilize them in order to ensure that they would not be degrading if we are increasing the temperature up till 1500 degrees Celsius. And graphitization is another process. In this also we heat them up to a very high temperature, and thus before treating the carbon fibers to high temperatures, it's quite necessary to stabilize them. And thus the first statement, which is an assertion, and the reason which is given for the same assertion absolutely correlates, and thus it's answer one which is correct. That is both A and R are true, and R is the correct explanation for the first statement. Fine. Everyone is able to follow me till yet, right? Do you have any doubts among all the questions which I have explained till now? Okay. Thank you. Yeah. So the next question stated that carbon fiber has seen limited success in metal matrix composite. And the reason for this assertion was given as atomic structure of carbon fiber is similar to that of graphite, constituting of sheets of carbon atoms arranged in regular hexagonal pattern. So both of these statements are true. Now we need to find if this particular statement is the right reason for this particular assertion. We already know that carbon fiber degraded around 400 to 450 degrees Celsius. So from literature also you'll see that these carbon-carbon composites or carbon fibers, they all uh, starts deforming, like degrading, when they are heated up till 450 degrees Celsius by reacting with oxygen. They form gaseous oxides like carbon dioxide, carbon monoxide, and similar ones. So if you are trying to make a metal matrix composite involving carbon fiber as the reinforcement material, then what you'll have to do is you'll have a carbon fiber as the reinforcement laid, then you'll add resin or the matrix material in liquid form for proper homogenization. So, for having metal in liquid form for proper homogenization, you'll at least have to heat that metal up till 700, 800 degrees Celsius. This is the minimum melting temperature of most of the metals which we come across. As carbon fibers already degrade at 450 degrees Celsius, it's quite difficult to let them not degrade at higher temperatures when the metal matrix is being poured on that carbon fiber's surface at higher temperature, which is equivalent to the melting temperature of these metal matrices. And therefore, these carbon fibers used in metal matrices are not commonly used commercially, and there are limited success seen because of properties of carbon fiber of degradation at lower temperatures. It's not at all related to the atomic structure of carbon fiber, which is similar to graphite. So you can see individually both these statements are correct, but when you actually try to find if this reason is correlated with this particular assertion, then you see that both of them are not proper explanations. So therefore the answer would be second, as both are true, but it's not the correct explanation for the assertion. Now, is it clear? Next, we have that properties of glass fiber are the same along the fiber and across the fiber. As most of you are mechanical engineers, you might already know that when we take a fiber, which is something similar to a rope, then when we apply force along the direction of the fiber, then it is known as longitudinal direction, and when we across it perpendicular to the fiber line, then it is transverse direction. So this particular question states that properties of glass fiber are same along the fiber and across the fiber. That is, its properties are same in longitudinal direction as well as transverse directions. The explanation behind this is given as that glass has a amorphous structure. So both of them are true. Glass is amorphous, and amorphous substances are known to be isotropic. And what means by having properties same in all the directions is actually isotropic material. So therefore, both of these statements are true, and this is correct explanation for this one, because amorphous actually means isotropic materials, and this is actually what is required for being isotropic material. So. Thus, this is also done. Then we have the eighth question, in which they are given different classes of glass fibers, and this is the list, which is the application or the properties of these particular glass fibers. Now we need to match what were the properties corresponding to each of these glass fibers. So these are characterized and even named based on their properties itself. For example, A glass fiber means which have high tolerance to soda or lime, that is, they are high alkali tolerant. Then C glass have high chemical resistance. D glass have low dielectric constant. E glass have low electrical conductivity. M has high tensile modulus, while S has high tensile strength. So out of this, S and D are directly there in this list. As we can see, S will have high tensile strength. Thus, C would be related to 4. Then D will have low dielectric constant, and therefore it would be related to 3. For explaining this further, I even have the composition of these particular fibers. So we can see E glass fiber with boron, E glass fiber without boron, ECR glass, then S2 glass, R glass, and quartz. So we can see here the S glass. S glass have high percentage of sand like silica, while the other constituents are comparatively low. And as therefore it will have higher strength as silica is far more strong as compared to the other structures. And this is this entirely depends on the properties of the like constitution which is formed out of the mixture of all these percentages, and thus if you know particular properties of all these like constituents, then you can simply compare that which property is higher and which influences this most. So on the basis of the percentage you can simply signify and find that which one would be the like constitution for which you'll have desired properties. So the ones which are expert with material science can use this particular data, but for solving this question, the common fiber categories and associated characteristics are also more than enough. Then when we see e-glass fiber, then e-glass fiber is a very commonly used fiber, and we know that e-glass fiber is used as glass fiber reinforced plastic materials quite commonly, and therefore e-glass would be matched with 2, that is glass reinforced plastics. Then C glass is chemically resistance. So chemically resistant fibers can be staple fibers as they don't actually serve the purpose of providing strength. So when they don't provide strength, we don't need continuous fibers to bear load uniformly, and thus having staple fibers will also serve our cause, because at the end they're only there to provide a like sort of inert atmosphere to the corrosive liquids which are stored within them. As this chemically resistant glass fiber composite which would only be used to store materials within themselves which are chemically more corrosive. So for this, you don't actually need strength. That is, you'll not be storing high compressed gases or something into this particular composite. You'll only be storing toxic gases, like not exactly toxic, chemically resistive gases or liquids within this glass fiber composites. And therefore, C glass can be staple fibers, and thus this entire column can be used as follows. So this is another table which indicates the properties of all these classes of glass fibers, and we can see density varies, tensile strength also varies a lot. We can see S glass has the highest tensile strength, and the same is being stated here that S glass is signified for its high tensile strength. Its tensile strength is 4.8, while the rest lie between 2 to 3. Our glass is also around 4, but nobody can match up till S glass, that is 4.8. Fine. Then let's move to the next question. Then, yes, yeah. So e-glass is very commonly used, and its cost is also less compared to the rest of the glass fibers. So you can see e-glass e-glass actually doesn't have a lot of modulus and strength, like it lies somewhere in between. If you want a composite which will have a very high performance in terms of its tensile strength, for example, you're trying to make ropes of bridges which will only have strengths in its longitudinal directions, like you'll apply force from both of these ends and there would be continuous composite made out of S glass fiber with a like thermoplastic or thermosetting resin matrix medium in between. So you'll have that entire composite. You'll stretch from both the sides. Then if the composite is made out of S glass, which has highest tensile strength, then it will break at a higher point because its tensile strength is highest. And if the reinforcement material is made out of this S glass, then definitely the performance and the tensile strength of that medium would be highest. But on contrary, if you are using E glass, then the tensile strength is 3.44. It's comparatively far lower as compared to S glass, and thus when applied in applications which involve lot of longitudinal stresses, then in those cases E glass composites will fail far early as compared to S glass composites. Is it clear? E-glass for commercial applications, what you see is its cost and its performance. Fine. So e-glass is used most of the places. Like it's the most common glass fiber which you'll find in composites which are made out of glass fiber, like bonnets of cars and all these daily use applications which involve this. Fine. And S-glass would be for high performance, which require a lot of tensile strength. Fine. So on that particular basis only you will see if you want to use carbon fiber, glass fiber or Kevlar fiber. The cost if you're working with commercial applications and the application for which it is oriented. Then the last question was that if this is the uh, yeah, yeah. What kind of mechanical properties do you intend to increase? Modulus or strength? Tensile strength. So in case of tensile strength, you can see this is the column for comparison. In this, the glass fiber which will have highest tensile strength, you'll try to use that one. Fine. So it's 4.8, which is S2 class. So this you'll be using. If cost is not at all your factor, then you'll simply go for the strength of individual reinforcement materials and directly use those for making the composite. Fine. Cost is issue, then you'll have to do an economical analysis. For instance, see, what you, how an actual composite looks like is you have a lot of fibers. Give like for one particular laminate. Let me explain to this slide. Just a second. Yeah, see this one. You can see here. This is our composite. This is a small part of a big composite. Okay, you can see here. This one is how it will look from top. You have a lot of arrangements of fibers at different angles arranged all together into a composite. So the first layer all has 90-degree angles. Second layer has 60-degree angles, while third layer has 0-degree angles. So if we want a composite which are with a required strength, then obviously a composite with single fiber layer would not be able to serve our purpose. We'll have to stack many layers one over another so that this entire structure as a whole can bear the load as per our requirements. Now, for instance, you want a composite which should bear a load of around 500 megapascals. Not 500 pascal, suppose, because we are talking about low strength materials. Okay. So if it's for 500 pascals, then you can actually see the strength which will be there of individual layers. You'll see how much stress this first layer can bear. The remaining stress would be transferred to the second layer. Then the remaining stress would be transferred to the third layer. Then the stress transfer and the stress bearing would also depend on the angles at which these fibers are arranged. The, for example, in this one, if this is 60 degree, then along this direction, it would this is longitudinal direction of fiber, but if you're applying stress in this particular direction, then only sine theta components will bear load, while cos theta component will only bear the transverse load, which would be negligible in this particular case because force is only applied in this direction. So the sine theta components of all these carbon fibers or the fibers which you are using would club up together to like provide support to this composite equivalent to this force. Now you will have to figure out how many fiber layers or composite layers should be there in this entire composite so that all the fibers when counted together like sine theta components of all these fibers, normal component like longitudinal components of all these fibers, this will give no contribution as longitudinal strength is all in this direction, and then we'll stack composite layer after layer. Once we find that how many layers are required for making this entire composite to bear a required force, that will be our composite. Now, if you are increasing the number of layers, the weight of the composite will increase. If you are increasing the number of layers, the cost will also increase. But if you are using fibers which will inherently have low cost. For example, carbon fiber is 8,000 rupees per kg. On the contrary, glass fiber is 200 rupees per kg. But carbon fiber will give strength which is around 3800 gigapascal, while glass fiber will give only around 1100 gigapascal. You can see the strength is almost triple when it comes to difference, but the cost is 8,000 and 3,000. So here you need to decide that you want a composite to have low weight or having high weight is fine with you. If having high weight is fine with you, you'll simply make a composite which comprises of many layers out of glass fiber and it would all be 200 rupees per kg and you'll have a composite which will serve a purpose. But the weight of this like this particular composite would almost be like two times more than what is there of carbon fiber. Are you getting my point? Like you'll have to compare. You want better weight performance or you can compromise with the cost. On that particular basis, you will choose what to give the priority to. Your choice of materials or your cost. Fine. Am I clear? Okay then. So yes, so this one is the last question. In this, they're simply given five normal reinforcement materials, and these are the properties of these particular reinforcement materials. So, sir has explained it quite well in class. Kevlar have the structure which is like benzene ring with amide ring. So this fourth is Kevlar. Then glass fibers are isotropic in nature. So B would be 3. Then boron fibers have large diameter and therefore its flexibility low. This is all already been taught in our lectures and therefore I don't think I need to explain it much. And alumina is a metal reinforcement. Its melting point would be far higher as compared to the rest of these fibers and reinforcement structures, and therefore it will retain its strength even at high temperatures because it will not melt or degrade even at high temperatures, while the rest will start degrading. So that's all. Uh, do you want me to discuss some other doubt? If you have, you can ask. Good evening. Yeah. Okay. See, refractive index is you might have learned in your 9th, 10th, right? It's the property of a material. If you try to pass light through it, then the amount of deflection it gives is the refractive index. So you can see all five, these are all glass fibers. You're talking about this slide, right? All are glass fibers. They are translucent in nature. Glass is like almost translucent. So when we pass light through this medium, so what happens is when light travels from one medium to another, which has a difference in their density, then if if this is the light, it's striking like this. there is a change in the density of the medium, then it will try to deviate towards normal if it's a more dense material, and if it's less dense material, then it will move away from normal. Like this is a very simple concept which we learn in school. And when we talk about glass fiber, they're all translucent in nature. So this is just a property which defines the like how can I say, the like ability of material to let light pass through it. Fine. As these are the property of glass would remain the same, there is only slight difference between the percentage of these individual components which are present in these particular fibers. So you can see there's not a lot of difference between its refractive index, but when you compare refractive indexes of different materials, like if you have glass, you have oil, you have water, then in those cases refractive indexes will highly vary. But when you see all types of different glass fibers, then refractive index will not vary much. This is a property which is used when you are dealing with radar absorbing materials or materials in which electromagnetic waves or light rays are involved. When you want to check how much rays it will let pass through it, then you'll consider refractive index into your consideration. If you are designing composites for enhancing mechanical strength, then you'll only focus on tensile strength, Young's modulus, and elongation at break. Fun. Okay. Any other question? Okay. Yeah. So see, for all kind of polymers, we define lot of temperatures. The like most commonly used one is glass transition temperature and melting temperature. Then we also have crystallization temperature and degradation temperature. But all these are not typically explained by sir. They are not much used when we talk about mechanical strength. When dealing with polymers for designing for mechanical applications, only glass transition temperature and melting temperature are the two temperatures at which the properties tend to change. So, you all know that polymers function through cross-linking, right? There are a lot of like monomers which are attached together using covalent bonds. They form a single chain. Then all these singles, like chains of polymers, are interlinked via uh, covalent bonds or hydrogen bonds. In case of thermoplastics, we have hydrogen bonds which are temporary, and in case of thermosets, we have covalent bonds, which is what cross-linking sir was talking about. Fine. You both, like, you all might understand these two topics individually, right? Do you have any doubts between what actually thermoplastics comprise of and thermosets comprise of, or else I should like explain from that start? It's fine with you, right? Okay. Yeah, yeah. So see, I'll start from the beginning. You have polymers. There are lot of monomer units clubbed together via covalent bonds. It forms a single chain of a polymer. Now, all these polymeric chains are placed parallel or in any like particular arrangement around each other. Then there can be two types. One in which there are covalent bonds. These are known as cross-linking, and this is how thermosets are formed. That is, they'll form rigid structures. Strong covalent bonds are there between parallel polymeric chains, and thus the polymer will not actually like deform and reform back based on like our wish, even if we increase the temperature or not. Okay, this is the concept of thermoset. That is, even if you increase the temperature, there will come a temperature at which it will completely break down. That is, the covalent bond, which is the interlinking between two polymeric chains, will start breaking. So now let's talk about glass transition and melting temperature. So in case of thermosets, we have only covalent bonds. So what is glass transition temperature is that all the temporary bonds which can easily be they are broken down so that the polymer, if it's initially there in the complete solid state, then it will start transitioning itself into a rubbery state. Okay, that is glassy state to rubbery state. So that is the glass transition temperature in which like all the bonds which are most easy to break, mainly the hydrogen bonds and all the temporary bonds which are there, ionic bonds and something similar, they'll all break down. That is the glass transition temperature. While melting temperature is that in which all the polymeric chains are separated from each other and they starts to flow. That is the state of the polymer changes from rubbery state to entire liquid state. That is, it like attains fluidity. So it starts behaving like a liquid. Fine. So in case of thermosets, we have proper cross-linking, which is covalent bonding between all these chains. If you try to break these covalent bonds, then obviously the covalent bonds which are there between the polymeric chains, that is between the monomeric units, will also start breaking. And therefore, in case of thermosets, when we try to like completely melt the polymer, then in that case it will completely degrade. It will not initially change into liquid state and then start degrading, but it will directly start from solid state, come to a like slightly rubbery state, and it will completely degrade. That is all the covalent bonds will start breaking up, and the monomer units will simply like break down into many. Fine. But in case of thermoplastics, you have a solid state, then you have a rubbery state, and then you have liquid state. Once you reduce the temperature of these thermoplastics, they'll again like realign themselves as per the requirements and then convert themselves again into their initial solid state. That's the difference between thermoplastic and thermosets. Thermosets are irreversible when it comes to polymerization, like solidification and remolding, while thermoplastics can again and again be remolded. So when Sir talks about like properties of these particular plastics at higher temperatures, that is its Young's modulus, its tensile strength, and when he relates it with the glass transition and the melting temperature, then this is the chemistry which he was talking about. Fine. So in case of thermoplastics, you see, you have thermoplastics. Initially, hydrogen bonds will start breaking at the glass transition temperature. Then at melting temperature, all the polymeric chains will separate out. There would be no cross like interbonding between these polymeric chains, and it will convert into a liquid structure. Once you remold it, it will again form the initial structure. And thus, when you increase the temperature, the tensile strength initially decreases a little. Then at glass transition temperature, it steadily decreases because all the interlayer bonding is no more, and then towards melting temperature it like decreases further. Fine. But in case of thermosetting, you won't observe this state of high change in tensile strength. That is because it comprises entirely of covalent bonds. Like most of them are covalent bonds. So when you try to like degrade it at higher temperature, then these covalent bonds will start breaking. So you'll not have a steady or high change when you're measuring the tensile strength at elevated temperature. This will steadily like come down, decrease, 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 and then at a particular point, the resin or the thermoset plastic would entirely decompose, and therefore the change in tensile strength is not much high in case of thermosets. Fine, because there is no melting temperature in thermosets. It's only glass transition temperature in which there would be small change seen, and then there is directly degradation temperature. But in case of thermoplastic, we get two peaks. One is at the glass transition temperature where temporary bonds, that is hydrogen bonds and ionic bonds are breaking, while in the second case, covalent bonds start breaking. So there would be property degradation at two stages. One is glass transition and one is melting. Am I clear?
Yeah, no. See, when you're dealing with mechanical properties, then this glass transition temperature would be very important because what you're seeing is you have reinforcements. Reinforcement are fibers. Okay, fibers are all binded together in a matrix medium. This matrix is a thermoplastic matrix or thermosetting resin or plastic, whatever you say. Fine. So mechanical strength is only there when the reinforcement materials and the matrix mediums are properly binded together, both in solid state. If there is glass transition temperature, what is happening is matrix is changing itself from complete solid state to a partially like rubbery state. Then what will happen? It will try to loosen its bonding with the reinforcement material, and thus what you'll see is reduction in mechanical strength. You're getting it? Once, if you have a solid which is holding something together, and one you have rubber which is holding something together, solid will provide higher strength, and therefore the SDP glass transition temperature is minus 87. Let me check. HDPE. Yes. Yeah. So amorphous behaves like thermosets. See, what I explained initially, that when you're dealing with thermosets, then there are only covalent bonds which you will be breaking. But when you're dealing with thermoplastics, there would initially be temporary bonds, which is hydrogen bonding, and then you'll move towards covalent bonding. So in case of semi-crystalline materials, you have a definite structure in which the polymer is initially arranged. That particular structure will not directly start breaking down. First, the temporary bonds which are there holding that structure together will start degrading. Once the temperature is beyond that particular energy level, then the actual crystalline structure will start degrading. Fine. So that's where semi-crystalline will also have two stages. One in which temporary bond which hold the crystalline structures together will break, and the second in which that entire crystalline structure will start breaking. Am I clear? And then in amorphous material, you have no proper arrangement. It's everything like laid down haphazardly. So therefore, these temporary bonds which hold some structure together are not at all present. So you can treat it entirely as all covalent bonds. Once you give a particular temperature, it will all degrade as it is and thus behave like thermosets. Am I clear? Thermoplastics which are amorphous. Yes. Yeah. Amorphous thermo. Okay, I'll check to it and then come back in the next lecture. Maybe. Fine. Yeah, yeah, I remember. Okay.
Yeah. Hmm.
No, it's amorphous. Yes. Yeah, graphite fiber, if you treat carbon fibers at a very high temperature, then their crystals reorient themselves in a better way and then that form crystalline fibers. So graphite fiber is just a post-processed form of carbon fibers, but it's highly crystalline in nature because in that carbon content is almost close to 100%. Fine. Yeah, if you want to make metal matrix composites, then you know that carbon fibers and glass fibers would not sustain because they have very low degradation temperature. But graphite fibers can go up till like higher range of temperatures. So when we want to make something out of aluminium 6061 alloy, which is normally used for hydrogen permeability, like making structures which are hydrogen impermeable. So in that case, if you are using aluminium 6061 as an alloy, its individual mechanical strength would be low. But if you embed it along with this graphite fiber, then you can have hydrogen impermeability and you can also have high strength. So in that case, you'll use aluminium 6061 as matrix material while graphite fiber as the reinforcement material. Right? Let me check. Even I'm not sure about it. What is it? But yes, sir in his lecture in itself discussed that graphite fibers are used along with AA6061. Yeah. Carbon fibers would degrade at 450 degrees Celsius. If you are initially making them with a process which does not involve directly treating those carbon fiber at 450 degrees Celsius, then it's not at all a problem. You'll have a matrix material which is something made out of ceramic, like silica carbide or something. Then in that case, you can use that at higher temperature because reinforcement are anyways trapped between matrices. It would not directly like react with higher temperatures, like oxygen around it. Fine. See, what I have worked on is glass epoxy, carbon epoxy, glass USP, Kevlar epoxy. I've never come across with metal matrix composites or carbon carbon. But I'll check it with someone and let you know if possible. Uh, Boron fiber. Yeah, most of them, the remaining one are amorphous. If you change the manufacturing process a little and try to have high purity in a particular fiber, then maybe you can increase its crystallinity because crystallinity is all about proper rearrangement of lattices together with highest purity possible. So I think it's like it more or less depends on the manufacturing process. As such, there's not a lot of difference between structure of like carbon fiber and graphite, right? Both are carbon, but the manufacturing process is what differentiates between them. What makes one amorphous while other crystalline. Anyone has some other question? Ajay, I'll check this thermoplastic amorphous and crystalline like similarity with one and let you know in the next lecture. Do you have some other questions or we can end this lecture? Yeah. Yes. It must be the impurities which are there. For example, you're making carbon fibers out of many things. One was rayon, one was polyacrylonitrile, one was cellulose. So the raw materials which you are using, you melt them all together, extract maximum amount of carbon which is possible, melt spin them, and then oxidize them. So this is how carbon fibers are made, and you also pyrolyze them. So there is some constituent which is left out of the initial raw materials which are used. So maybe that's present. Oxygen can be there because oxygen is always there whenever you are like producing something at a commercial stage, because you cannot actually have an inert atmosphere completely. I'm not much idea. I'll check this time. Okay. See, um, how I remember is, if you're talking about thermosets, then when you try to purchase it, it will always have two constituents. One is the like actual material, the other is the hardener, that is the cross-linker. If the like polymer you are making involves two constituents which you are placing together, then most of the time it's thermoset. But if there is some powder, you are heating it at a higher temperature, trying to melt it and then remold it, then it's always thermoplastic. So this is common thing which you can remember. And apart from that, there is also like the most common thermoset which we come across are polyesters, epoxy resins. When you're making composites like and phenolic resins, so these three are the most commonly used thermosetting resins, and thus commercially will come mainly across these three only. There's also peak, but yes, most of them involve epoxy constituents because you need to form permanent covalent bonds. So you need to have unstable rings within themselves so that they'll readily start cross-linking as soon as hardener is mixed. Fine. As such, there is no hard and fast rule. Just have to see the chemistry. Fine. Okay.